So let's take a look at what the addition and subtraction properties in section 2.5 say. So here's my given diagram. Hopefully it's obvious, right? AB has a length of 4, segment CD has a length of 4 as well. So we could say that these segments are congruent. Okay, so now look what I've done. I have taken this segment of AB and I've added BC to it. So I've added those two pieces and I say that this whole segment right here, that's what I was doing in the green. I got that segment to be a length of 6. And I could do the same thing on the other side. I can add those two together and get that is a length of 6. So I went from having smaller congruent segments to getting bigger congruent segments. How did I do that? I added the same segment. I added BC here and I added BC here. I added the same segment to both sides. All right, shrinking that down a little bit, here's our new theorem now. If the same segment, and what segment was it? In this case, it was BC. If the same segment is added to congruent segments, remember these guys were congruent up front, then the sums are congruent. So that's basically your addition property. Now, I also have to note that this could say angle. This theorem is still the same. It still holds. If the same angle is added to congruent angles, then the sums are congruent. So here's our first addition theorem in the section. Okay, so let's mix it up a little bit and take it a little bit further. So now I have the two segments, and let's just put in numbers right now so we could see it. So here's what I'm saying. These guys are congruent, and these guys are congruent. So these are little segments, these are little segments. But I can add the two little pieces. That's what I was doing here. I can add these two pieces and get the entire thing to be 6. Same thing down here. I can add the two little pieces and get the entire thing to be 6. So, let's take a look at the new theorem we just discovered. If congruent segments are added to congruent segments, what's that mean? These guys are congruent. Let's add them to these guys because these guys are also congruent. So if congruent segments are added to congruent segments, then the sums are congruent. That's the 6's. So basically, if the 4's are the same and the 2's are the same, when I add 4 and 2 here and I add 4 and 2 here, I get the 6 is the same. Now this is all easy with numbers, but later in the proofs, we're going to take away those numbers and we're going to be talking real generally like this. Okay, one more time. I should note that this will also hold for angles. So if everywhere I see the word segment, I change the word for angle or angles, depending on what fits, it will also hold. So if congruent angles are added to congruent angles, then the sums are congruent. And there's theorem number 2. All right, so let's flip that around a little bit. So let's say this time I'm giving you that segment AC is a full out 6, and I'm telling you that BD is a full out 6, and I'm telling you this itty bitty little BC is just 2. So here's my given. What can I do with these two pieces? I can subtract the two pieces to tell me what the length of AB is. So if I go 6 minus 2, that's what I've done here on the left side. If I go 6 minus 2, I get that AB is 4. Okay, well fine. I can subtract on the other side, and I can take this 6 and I can minus the 2, and I can get that CD is also 4. So we subtracted, and we've got from these big segments, so the 6 is the biggest number up there, from these big segments we subtracted the same segment, so this BC got subtracted off the left side and BC got subtracted off the right side, and I was left with smaller congruent segments. In other words, if the same segment, and in this case it was BC, that was the segment that was the same, if the same segment is subtracted from congruent segments, then the differences are congruent. There's theorem number 3. Okay, as you probably expected, we do have one more case of the addition subtraction, so look what I've got. I'm giving you that this entire segment is length 6, this entire segment is length 6. This itty bitty one's a 2, this itty bitty one is a 2. So what can we do with the 6's and the 2's? We can subtract them. If the 6's are the same and the 2's are the same, then when I subtract them, I'm going to get an answer of 4, which is the same. Okay? That's basic arithmetic. If the wholes are the same and we subtract off the same amount, yes, the differences are going to be the same. So what does that look like? That looks like this. If congruent segments are subtracted from congruent segments, then the differences are also congruent. Okay. Since the 6's were congruent and the 2's were congruent, the differences are congruent when I subtract them. Done. Okay, let's switch into section 2.6. So 2.6 deals with multiplication and division. At first, I think it's a little confusing for kids trying to distinguish between addition, subtraction, and multiplication, division. Okay, usually a really big indicator that it's multiplication and division is right here. It deals with midpoints or bisects or trisects. Okay, if these statements are not present, then it cannot be multiplication and division. So let's take a look at what our given is telling me. My given is telling me that AB right here is congruent to DE right here. Okay? But then it's telling me that I've got a midpoint here and a midpoint here. Okay? So everybody's first thought is because this is the midpoint, then AB is congruent to BC. That is absolutely true. If a point is a midpoint, then it divides a segment into two congruent segments. But that's not really the direction I'm going for here. I'm kind of looking at it like this. If these two halves are congruent, okay, and I know that this is the midpoint, so I know this is exactly half and this is exactly half. So if these two halves are congruent, then the bigger wholes must also be congruent. Okay, so this is what I just said. This is our idea here. If the little guys are congruent, and we know that these are in fact midpoints, and I take this and I double it, okay, and then I take this one and I double it, then the wholes must be congruent. And if you're still not seeing it, put numbers in. So let's say that this is a length of 3 and this is a length of 3. Now remember, we've got a midpoint. So if this is 3 and we double it, that means that the whole thing is 6. And same thing on the bottom. If the little piece is 3, then the whole thing is 6. So we can see that when the 3's were congruent and we doubled them, we got the 6's congruent. All right, so this is kind of how we think of it, but how do we formally write that? So here's our new theorem. If two segments are congruent, that would be the two that we called the 3's, the AB and the DE, the little guys. If two segments are congruent, then they're like multiples are also congruent. Now you can't use multiples again unless you have midpoint, bisects, or trisects. You have to have something that allows you to double it or to triple it or to quadruple it. And this is what allows me to do that. Okay, and just as we expected, if I flip it around and I give you the wholes are congruent, so AC is congruent to DF. But again, I tell you that these are midpoints. What do midpoints do? They divide things. Okay, yes, I can get the left and the right side here congruent or the left and the right side here congruent, but that's not my goal. My goal is to say, look, if these two big segments are congruent and these points really cut them in half, then the smaller halves are congruent. So that gets me that AB is now congruent to DE. So again, it's this idea that the wholes, if the wholes are congruent or congruent wholes, leads me to congruent halves. Formally, how do we say that? If two segments are congruent, and that's the wholes right now, then they're like divisions are congruent. So hopefully this will be a nice summary for you here. If you are starting with small segments or small angles in the given, okay, you have small pieces, and the proof statement or the direction you're going asks you to find bigger angles or bigger segments congruent. Okay, there's two options that can get you from small to big. It's either addition or multiplication. On the flip side, if you're starting with or if you're given big angles or big segments and you're asked to go to small angles or small segments, it's going to be subtraction or division. So first you have to figure out, well, what direction are you traveling? Small to big or big to small? Okay, fine. So now let's say you're going small to big. How do you know if it's addition or multiplication? There's a quick answer to that. Okay, multiplication requires bisects, trisects, or midpoint. Okay, it doesn't have to have all of them, but it has to have one of those things. And it has to have two statements of bisects, or two statements with trisects, or two statements with midpoint. Okay, one for each of the small to big segments or angles that you are dealing with. So two bisect statements, two trisect statements, two midpoints going small to big, that's going to be multiplication. Same thing holds on the other side. If you know that you are going from big angles to small angles or from big segments to small segments and you're not sure subtraction or division, look for bisects, trisects, or midpoint. If you have two bisect statements, two trisect statements, or two midpoint statements, it's probably division.